Hello everyone, it's November 9th. Alright, before we start, I read the proof. I left some comment, so it's a good proof. I think I am convinced. Basically, what it's trying to do is to prove that when the number of columns is smaller than 6, then if any good subsets exist, then within this good subset you have at least one pair that's also a good subset. So we can just reduce the whole problem to finding any pair whose and becomes 0. So that's basically the whole proof. And the way to prove it is they first suppose it's a proof of contradiction, right? We suppose that there exists a certain number of good subsets, that within this good subsets all the pairs are bad, right? None of those pairs are good pair, and you can prove quite easily. I shouldn't say quite easily. You can prove, but it's left for the reader that if you exist such a number of pairs, and if such a number of good subsets, if it's a odd one, then you can always get down to even. I think that's easy to prove. So you can get 2k, right? So basically we say we have 2k number of rows that are good subset, and then we want to satisfy that, right? Which means you have at most k ones on each column. And then we also suppose that within this 2k rows, none of the pairs can form a good subset, which means you have at least one column that have 2 ones, right? So you have these two conditions. And in order to satisfy these two conditions, they prove that there must exist at least 3 ones for each row. And I'll skip the proof here, but it's a pretty good proof. Like I buy it, the proof. So now what we have is, in order for these 1 and 2 to satisfy, you have to have each row at least 3 ones, right? And then I think the author kind of goes a little bit too fast to reach the conclusion. That's why I write this, right? So what I say is, if we want to have these 2k rows to be a good subset, then you have at most k times n ones in within this 2k rows. And we also prove that you have to have at least 3 ones in each row, right, for the 2k good subset. So at least three ones, which means you'll have at least 6k, right? At least 6k number of ones within these two. So one condition says we have at most kn, so it's smaller or equal to kn. And the other said we have to be at least 6k, so it have to be larger or equal to 6k. So for these two to satisfy, then the kn must be larger or equal to 6k, or the n, or the number of columns, has to be larger or equal to 6. But the problem has a restriction n equal to 5, then which means one of the 3 or 4 must have contradiction. Now 4 is the definition, so the only contradiction can be in 3, which means given any 2k subset, we cannot find all the pairs to be bad. They at least have one pair to be good, which is the foundation of our solution. And also means if we have n larger or equal to 6, then we cannot find, right? There will exist 2k good subsets where all the pairs are bad, and this is one example, right? N is equal to 6. This is a 4, right? Subset of len of size 4, and it works because each column have at most 2, but none of the pairs are good. So if it's equal to 6, then it's not 2. And I believe you have to expand it, right? You have to expand it. Instead of finding 2, I think you have to find the minimum. I think becomes 6. It becomes 4. But we're not gonna worry about that. It's a good one. The proof is not that easy, honestly. All right, I'll leave this one here, and we're gonna try to solve this problem. I'll do a fast one because I'm hungry. Okay, I'm hungry. All right, restore the array. Okay, so this is a medium, so we have to go for Java. There is an integer array nums that consists of n unique elements, but you have forgotten it. N unique elements, but you've forgotten it. However, you do remember every pair of adjacent elements in nums. You're given a 2D integer array, adjacent pairs of size n-1, where each adjacent pairs I indicates that elements ui and vi are adjacent in nums. It is guaranteed that every adjacent pairs of nums will exist in adjacent pairs, either as this or this. The pairs can appear in any order. Return the original nums. If there are multiple, return any one of them. That's actually quite interesting. So let's see the first one. So we have 2, 1, 3, 4, and 3, 2, right? So we don't know the original order, and this can be any order. So we just need to find one of size 4, right? So we just need to find something of size 4 that with adjacent, okay? So we can definitely find something. I mean, this we can just be, what should I call it? Degrees, right? So 2 has degrees of, this is 1. 1 has degree 1. 3 has degree 1. 4 has degree 1. And 3 has degree 2. 2 has degree 2, right? Therefore, 2 and 3 must be in the center. 1 and 4 must be at the on the outside. And I don't think it matters. No, it does matter, because 2 doesn't have anything with 4, but 3 has with 4. So yeah, we can just go with this. So 1 must be at this, 4 must be at the end, right? And then we can just go to these two. Who's connected to 1? 2 is connected to 1. Who's connected to 4? 3 is connected to 4. And boom, we're done. So we can probably get a adjacency list, right? It's adjacency list. What's the size? 10 to the 5th. Ugh. Not adjacency list. Come on. The values. We need the values. So it's going to be a dictionary, right? So 2 will get to 1, right? And then 3. 1 will have 2. 3 will have 2 and 4. And 4 will have 1. So once we get that, we need to go through the whole thing, find the ones has only 1, because they will definitely be on the end, on either ends. And then so we put 1 and 4. So we know there's 4, right? We know that. So 1 and 4. And then we just say for 1, next is 2, right? So we need to find what's the next one for 2. It cannot be 1, so it has to be the other one. Oh yeah, it's only 2. There's only 2. All right, there's only 2. So you can just say, yeah, I just pick one that's not equal to the parent. So yeah, it's gonna be 2. So yeah, you go for 1, right? You put these, and then you start from this, and then you start from 1, and then it's a 2, right? Then you put 2 here. You start with 4. It's 4 is not a 1. 4 is 3. So that 4 is going to be a 3. You put here, right? And then if this we're done, right? If it's not, then you say 2. You're going into 2, right? And 1 is already used. We can have it like a scene, okay? So 1 is, or we have a pre. Yeah, I think pre is easier. We have a pre, right? Pre is equal to 1. So we go for this. 1 cannot do, so we have to go to the second one. There's only 2, so we can just go to 3, right? So you put it, and yeah, you can do that. All right, let's do this. It's not too bad. Oh my goodness, this is absolutely bonkers. I'll do that. Delete that. Okay. I'm thinking like whether it's possible to not do adjacency list. I don't think it's possible to not do adjacency list though. Right? How are you gonna exactly how are you gonna do it without adjacency list? You have to go through the whole thing to find. Yeah, you have to have adjacency list. Okay, it's alright. I'll just do adjacency list. Okay, so we need to have a, what the hell? Alright, so what's that? It's a hash, it's a map, right? Map gonna be integer. Oh, I intend to do a list. I want just to do an int, but I don't really think an int will work. So yeah, this is how I do. This is just graph, right? New hash map. That's fine. So we get a graph. What else do we need? We don't need anything else. So we say for int tuple of adjacency pairs, right? We say graph dot put if absent. Put if absent what? Top 0 new array list, and we'll do the exactly same thing. Top 1 put if absent. Nah. Yeah, it's okay. Then graph dot get. Yeah, because you have to put it first. You cannot get a default, right? So we can get top 0 dot add top 1 and graph dot get top 1 dot add top 0. I feel like there are easier ways to do this. I don't remember, but it's okay. So we'll do that, okay? And then we need to find for we need to have a res, right? Res equal to new int this dot length plus 1. Right, perfect. Then we can say for dot val. Wait, how do I do that? How do I get the values of graph dot values? Right. So for be a list integer list of this if list dot size is equal to 1. equal to 1, then we need to set, because there will be 2 of them, right? What do I do? Int I is equal to 0. Then we say res I is equal to, oh yeah, I and j. Int j is equal to res.length minus 1. Perfect. So if that's equal to 1, then we say if I is equal to 0, right? Then res I will equal to, we need a couple of more things. Okay, we need a couple more things. It has to be entries, because I need the keys. Alright, might as well just get keys. Key set, sorry. Integer key, okay? And we shall say graph.get key.size. That's fine, right? So if I is equal to 0, res I will equal to key. Okay? And then I will plus plus. And then we'll say else res j minus minus will equal to k. And break. Does that make sense? I don't really think so. I think we should do this. Right, so the first one I get is so it could be any directions. So that's why I set the first time that it become 1, I set it. Okay? And the second time become 1, I will not be 0, so I set j. Now if I set j, so I and j, we also need pre-left and post-right. Okay? Pos pre-L and the post R. So I need to do this one as well, because I need to record the previous value. It's very important. Pre-L will equal to K. Okay? Post R will equal to K. Done. Okay. So now with this done, we shall say while I j minus I is larger than 1. Right? J minus I is larger than 1. What do? We will say find the pre, right? We have the pre-L. Then we'll handle I first. Okay, how do I handle I? We have graph.get pre-L, right? .get pre-L. And we have the 2. We can say list integer children. Can actually put it here. Okay, list integer children. So we can say children will equal to this. Right? It will be initialized. But the thing that they don't know, so I just put 0 here. doesn't matter. All right, so we get this. And now we say if children.getAzero is not equal to pre-L, then we say what? We say res I++ will equal to children.getZero, right? That's where we're gonna put the next for the I go forward, and pre-L will equal to children.getZero as well. Else, then exactly the same code, but now it's going to be .get1. And we'll repeat the entire thing. So we get post R, right? And then we say children.getZero is not equal to post R. Then this is J. Wait, what the hell? Duplicate code fragment. How would you suggest? Huh. It's alright. This is gonna be J minus, right? Or equal to that, and then post R equal to this. Otherwise, J minus equal to this, and post right equal to this. And then once we're done, now we can return res. Okay, let's give this a shot. Let's see, is this correct? Ooh, what the hell? That is bad. That is very bad. What happened? Why you get out of 0? I don't understand, but it's okay. Let's just take a look. What did I do wrong? Oh Lord, we have to do this. JSON pairs. Two, 1, 3, 4, 3, 2. I have no clue. Dot to string. Array dot to string. All right, so what we need to do is put this one here and then debug it. All right, what the hell happened here? J minus I larger than 1 is false. Oh, what do you know? What do you know? Because the way you set them up. You add them, then they will go. Right? You add them, then they will go. So they will meet in the middle. So I think I need to change this. Yeah, this is not right. So while J is larger or equal to I. Right? Will this work? Yeah. Okay, so I change this to J is larger or equal to I. Good. Can we have like a odd number? Let's do one more. we can put one more here. So let's say put a 5. So we have a 1, 2. Let me have to rewrite this again. So we have 1, 2, right? 3, 4. Then 2, 5. Right, and then 5, 3. 1, 2, 3, 4. Yeah, let's see. That one works. Ooh. The last one, we have issue. How come the 4 comes up again? All right, let's do this. Good. Yeah, we localize problem. 1, 2, 3, 4. Right. So we have 1, 2. So 1 we have 2. 2 have 1. 3 has 4. 4 has 3. 2 has 5. 5 has 2. 5 has 3. 3 has 5. Right. So we noticed this is 1, this is 4, okay? Now 1 have 2, 2, so we can go, so 1 has 2. And 4 has 3. So now look at 2. 2 has 5. And 3 has 5 as well. We should put this as 5. How come my output 2 is going to 4? That is very interesting. Well, I think I don't know. Well, you don't need to know because there's something called debugger. Let's just go through the debugger and take a look. What was wrong? So 1, 2, 3, 4, 2, 5, and 5, 3. All right, let's debug this thing. Right, as 1, 3, we have res. Yeah, 1, 3, that's good. Children, this is 1. We get size is 1. What's the children then? It's a 2, right? 2 is not equal to, so we get it. So we set a 2, I equal to 2. It's good. 3 is equal to 2, right? And on the right hand side, we get 4. 4, 4, 4, 4 will get 3. Right, so we get 3. Perfect. So now they're the same, right? They're the same. And children. Okay, what's the children? Children have 2 things, 1 and 5, right? 1 and 5. And the pre-left is a 2. Pre-left is 2. And I have 1 and 5. Pre-left is a 2. Pre-left should be 1. Oh, we have a logic issue. Pre-left should be 1, right? I'm at this. So pre-left is 2. I don't even need a pre-left. I think that's kind of tripping me. I don't why do you need a pre-left? That doesn't make any sense. Right? These don't make any sense. We don't need it. We absolutely don't need it. Right? So we are at ij, right? So the children is just going to be res I minus 1. That's the children. And then what we that's the previous. And what we need to do is just check this is not equal to res I minus 1. Right? So you're at I is equal to 2, 0, 1, 2, I is equal to 2. and previous is 2. And then it should not equal to, we're trying to say is this, right? The current one should not equal to this minus 2. Minus 2. Do I even have a minus 2 to begin with? We don't. We don't have minus 2 to begin with. Then what? Then we say or, right? If I minus 2 is smaller than 0, or this. Just to handle the first one. Alright, just to handle the first one. You know what? You know what? We can reduce that. Right? I think we can. Hold a second. Hold a second. We can do that. So we set to 0, right? And then we can even do res I plus plus again. That shall equal to graph.get k dot get 0. Res j minus minus will equal to graph.get k dot get 0. Boom. Then we hit this. Then we don't need to check this one anymore. Then it's just going to be I minus 2. If it's not equal to, we'll get it. If it is equal to, we'll get the other thing. Right? And then this is the same. So this will be res j plus 1. And if it's not equal to j plus 2, right, then we'll do this. We'll do this. Run it. There we go. So I think this has legs, and in order to do that, I can also remove this just to save some lines. I actually did not save any lines because we have an else. It does save lines because I don't need this. Boom. All right. I can probably even do it this way. I can say res I plus plus. Oh, we probably cannot. Because when you do that, nope. Explicit is better than implicit. I think all I will do is just remove this. Save like 2 lines. Okay. I think this one shall be right. Yep. Have you tried? I've tried 2. Yeah, we'll try even. We try odd. I think we're good. Oh, what if? Oh, it's unique elements. So we're good. We are good. Yep. It's pretty good. One 743. Adjacent numbers essentially form an edge. We can identify the number on both ends, on either end, by finding the number with only 1 degree. 1 degree, right? Only 1 degree. Then starting from them, we can populate the rest from both ends. From both ends in, right? Very efficient. Okay, both ends in. That's it. ON. There's no search. There's no nothing. It's just create, initialize the first, and then deal with the rest. Good runtime. Good runtime. All right. I think I want to know, all I want to know is if there is a better way to set up this. DFS. This is not DFS, and this is BFS. Oh, I guess DFS will work as well. All right. You start from 1, and then you just, we can do, yeah, we can do that. We can definitely DFS this. Ours is even worse. This is even worse. I like mine. Put if absent. Get a root. Get answer. DFS. Beautiful. Very beautiful. Follow the path. Yeah, you can iterative as well. You just have to check. Okay, good. That's a good problem. This is what I consider medium. This is definitely as medium as it can get. I mean, with Java, sometimes I don't. I become a little bit more cautious with recursion, because recursion does cause stack, and I hate heap. Right? It requires heap, and sometimes heap space is not as big as stack. I think not as big as just iterative. Right? That's kind of my current understanding. You want to do that? I don't. Honestly, I do not. We'll do this when we have an easy problem. I want to do an easy one. Just call it a day. Ugh, and this problem. Jeez. Flatten. I know. Parallel. Yeah, I still have to do this to parallel. I think I kind of forgot how this one is done again. Come on, man. It's the earliest that each node can go, right? So we need to start from all the nodes, because it's a DFS solution, so we don't consider which one is the first. So we start from any nodes, and we try to figure out what is the latest time that I forgot. Wait, hold a second. We're BFS from each node, and what we want to see is the max time it will take. For here, the max time is going to be 3 months. I think it's starting from each node and then finding out the max time and then take to finish this class. So if we start from this, let's say this will be 5 months, right? And then we start from here, we say, okay, this is in 2 months, then we need to know the max time that this is going to take. And this will tell me is 5 months, right? So this will be 7 months. And the max time this will take is 12. Yeah, I think that's the one, right? That is the one. At each node, we try to find out the max number of time that this one will take. And then we collect it. Maybe we'll do this, you know, just to get it done. You want to Python it? Sure. Why not? It's a hard problem. So how would you Python this? So what we need to do is, given some DFS, right? So we have a node, and we need to return an int. But we need relations, right? We need relations. So that's a adjacency list. So we need a graph. I remember it's, you see, if you don't do it, you kind of forget about things. So I remember it's a default dict of list for AB in relations. I think it's graph A dot append B. Right? It's a one way. Okay, so that's the graph. Now when graph is done, so we also need functools. We need to cache this thing. So this one will have n ARU cache max size or equal to none, right? So given a node, we're gonna find the longest time it's gonna take, right? So what we need to do is to find t or equal to time node, right? And then for child in graph node, actually no, t shall be 0. Yes. Yes. What if it doesn't have? Yeah, t equal to maximum t and DFS child. I will return t plus time node. So that's DFS, right? Then we will go from everything, everybody, right? For when you say rest is equal to 0, right? Nah, not rest, just equal to maximum for node in range and oh dear me, I remember we have to do this because it's 1 to n. Stupid. We'll do this and we base a DFS node. Oh, we can just return this. Let's give this a shot. Does it work? Ah, I think it does. DFS from any node to find the max time it will take to complete the any course, right? If I want to take to complete a course, the answer is the longest time, right? That it will take the longest time to finish any course, any single course. And it's gonna be O. Well, then how many nodes you have to do? N V plus E. I think, because you have to go through this. So it's v plus e. Go. Should be fine. Yeah, should be fine. Oh, look at the difference. Look at the difference. So did I do bottom up or top down? Yeah, I have a DP. I have a DP. I have a DFS. Yeah. 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 Yeah, it's the same. Okay. We're good. I can turn this off.